In this video, we want to figure out how does sampling rate conversion work when we want to increase the sampling rate. This process is also referred to as interpolation. So what is the problem we are interested in? We are given a sequence xn which has originally been sampled from a continuous time signal at a sampling rate of 1/t hertz. So we have this x of t, and we passed it through a continuous to discrete block, and we got this xn. And what we want is that we want to somehow process this signal xn to obtain another sequence xin, I for interpolation, such that the final signal that we get, xin, appears as if it was sampled with a sampling period of t/L. So we want something xin, it appears as if it is obtained by sampling this signal x of t with a sampling period of t/L, or sampling rate of L/t. So effectively, we want to increase the sampling rate, or equivalently, we want to decrease sampling time. Now, what we have learned so far is we have learned how does an upsampler work, which basically takes a sequence and expands that to a bigger sequence by adding zeros into that. But that block itself is not going to give you this interpolated signal. So the purpose of this video is basically to derive what exactly do you need besides the upsampler block. So let's begin by looking at what is it that we want. We want to have a process such that it appears as if x of t was sampled with a higher sampling rate. So we have t equals nt/L to get xin without actually going to the continuous domain. Okay. Now, since this is what we want, this means that in frequency domain, we need the following relationship. If I denote the dtft of this xin as xi of e to the j omega, then from our previous knowledge of sampling theory, we know that whatever process we do, whatever we do to the sequence, whatever we do to this sequence xn, the new sequence xin that we get must satisfy this relationship. We should get xi, which is given by 1 over the sampling time, so it will be L/t. And then we need multiple copies of my original Fourier transform of my continuous signal, which is scaled by the sampling time. So the frequency is scaled, so this will be capital T times L, and it is shifted, the multiple copies are shifted by multiples of 2 pi k. So keep this in mind that we are after deriving this relationship. This is what we need. Okay? I'll call this the expression star. Okay, while we want this relationship, so far the only block we have learned is that we have xn, and we can pass it through this upsampler L, which is also called an expander because it expands the original sequence to get xen, which is defined as x of n over L for n from 0 plus minus L, so multiples of L, and 0 otherwise. So this is the upsampler that we have, which effectively just inserts zeros between any two samples. We are interested in this star relationship, so what we are going to do is we are going to first find out what is the Dtft of this expanded sequence as a function of xn and then as a function of x of t. And then we'll see how far away we are from actually our desired Dtft, and we will see that a simple operation will then get us to the desired Dtft. So let's start with that setup. So what is the relationship between the Fourier transform of my original sequence x of e to the j omega and my expanded sequence xe of e to the j omega? This is the first thing I need to find out. Now to do that, I am going to basically write xe of n as a summation. So I'm going to write xe of n as a summation involving delta functions. So I'm going to say k from minus infinity to infinity, x of k, delta of n minus kl. This is just a mathematical way of writing whatever expression we got over here. What this is saying is that at n equal to 0, you have a delta function whose value is x of 0. Then everything is 0. And then at n equal to L, I have another delta function whose value is going to be simply x1. Okay? So if I have, let's say if this is my expanded sequence xen and my original sequence was just length 2 sequence xn, then I know that xen, this is simply x of 0. So I can write this as this is x0 multiplied by a delta function, and this is simply x1. And everything in between is 0. So this expression is just a way of writing this thing in a compact form. Okay. Now, why do we want this expression? Because it helps us compute the Dtft of the expanded sequence much easily. So remember the Dtft formula, it's n from minus infinity to infinity, xe of n, e to the minus j omega n. Now I'm going to simply plug this version of xen into this formula, so I get a double summation, n from minus infinity to infinity, and then k from minus infinity to infinity, x of k, delta of n minus kl. This is my xe of n, and then I have e to the minus j omega n. Okay, what I'm going to next do is simply do a change of order of the summation. So I'll take k outside, k from minus infinity to infinity, and x of k, and then n from minus infinity to infinity will be inside. Since x of k does not depend upon n, I have taken it out, and then I get delta of n minus kl, e to the minus j omega n. Now let's stare at this. This we will simplify by using the following property of the delta function. So remember, if I am given n from minus infinity to infinity, delta of n minus n naught, and a function of n, f of n, I simply, by the shifting property, I get f of n naught, and then I get n from minus infinity to infinity, delta of n minus n naught. And since this whole summation has only one delta, so there is only one of the terms of this is non-zero, everything else is 0, the summation of this is going to be 1. So I simply get f of n naught. So I am going to use this relationship to solve this. So the first summation comes up as it is, x of k. Now the second summation, I will get f of n naught, just this expression. So I'll get e to the minus j omega, and n naught in this case is k l. So I'm going to write it now in the same form, but just rearrange the terms. So I'm going to get x of k e to the minus j omega l k, or I could write this also as k from minus infinity to infinity x of k e to the minus j omega k, where I am replacing omega by omega capital L. Now what is this thing? What is this expression inside before I change the value of little omega to little omega L? Well, that is nothing but the Fourier transform of my original sequence x of e to the j omega. The only difference I have here is instead of xn, I have xk, but that k or n, that's just a dummy variable. So what I get is that the expanded sequence x of e to the j omega is simply x of e to the j omega, with omega replaced by little omega L, or that is equal to x of e to the j omega L. So what that means is that when we use an upsampler, what that does to the frequencies of my original sequence is it simply scales my frequency axis by 1 over L. It effectively compresses my frequency axis. So you can think of it also in terms of duality. By expanding the sequence, you're increasing the length of the sequence, and the effect of that is happening in frequency domain, that your frequencies are becoming compressed. So this is the expression that you are getting. We now have to look at it more explicitly. So what expander is doing is it's scaling frequency axis by 1 over L. So let's take a look at a simple example before we go further and connect it to the interpolation expression. So let's assume that we are given a sequence xn whose Fourier transform looks like the following. It's this shape where the height is a and it goes from minus pi to pi, and then there is periodic repetition. And let's assume that we upsample that by a factor of 2. So what do we get according to this expression is the following. So the frequency axis basically gets scaled by a factor of 2. So what we get is that this pi expression actually comes at pi by 2 and minus pi by 2. The height stays at a. And then, of course, this 3 pi goes to 3 pi by 2. So what we will have here, and this 2 pi expression and minus 2 pi. This 2 pi expression actually goes to pi. So our relationship, our main Dtft will take this shape, and then of course there is going to be periodic repetition of this thing. So you will get up to 3 pi, you will get periodic repetition of this, and then you will get up to minus 3 pi. Okay, so if you look at this, what you see is that all the frequencies, when we have done expansion by a factor of 2, all the frequencies have been compressed by a factor of 2. In particular, if you are looking for whatever was this sort of Fourier transform, you are getting that over here in a compressed version, but you are also getting something additional, which you can think of it as an additional copy. In this case, you have L equal to 2, so you are getting 2 minus 1, effectively one more copy of frequencies that you did not want. So we'll formally come back to that part later as to how to get rid of these copies, but this is just a pictorial representation of what is the relationship between the sequence that I start with, its Fourier transform, and the downsampled version of that sequence. Okay, so how far away are we from getting to our objective of increasing the sampling rate? Well, to see that, remember this relationship. If xn has been sampled, we have x of e to the j omega as a function of the Fourier transform of our continuous time signal as 1 over t, where assuming t is the sampling time, k from minus infinity to infinity, x of j omega minus 2 pi k over t. So we know that relationship. Now we know also the relationship between this sequence and its upsampled version. So all we have to do is just replace omega by little omega capital L, and we will get back the Fourier transform of our expanded sequence as a function of our continuous time Fourier transform. So what we get is x e of e to the j omega 1 over t, k from minus infinity to infinity, x of j, replace little omega by little omega L minus 2 pi k over capital T. I'll simplify that a little bit further. So I'm going to write x of e of e to the j omega, that's 1 over t, summation k from minus infinity to infinity, x of j. I'm going to take this L outside, so it's going to be 2 pi over L k times L over t. Okay. So when we have this expression, we started with x of t. We did a continuous to discrete conversion with time period t to get xn. And then we upsample it by a factor of L to get x e of n. When we have this expression, then we see that the relationship between x e, the expanded sequence, and the Fourier transform of my original sequence, or my original signal, x of t, is given by this relationship. But what did we want? Remember, what did we talk about that we want? What we want is this expression. If you compare the two expressions, so we have the magnitude, what we want for the interpolated signal, so that I can change the sampling rate exactly by a factor of L, we see that the magnitude needs to have a capital L in there, and then there should be a change of frequency axis, and everything should be shifted by multiples of 2 pi k. So let's see what we are getting. Okay, so if we compare, we are, instead of L, we are getting 1. So issue number 1 is there is no L in amplitude scaling. And the issue number 2 is that the shifting, instead of by 2 pi, multiples of 2 pi, the shifting is by multiples of 2 pi over L. Now, as far as the frequency axis scaling goes, that is correct. The frequency axis scaling needed to be by T over L, or in this case, L divided by T. So T needs to be in the denominator, we have there. L needs to be in the numerator, we have that. So that is not an issue. We have multiple copies, that is not an issue. We have a T over here, that's not an issue. The only 2 issues we have is that there is no L in amplitude scaling, and shift is by multiples of 2 pi over L, which means that we are getting, due to issue number 2, we are getting L minus 1 additional copies of x of j omega. We are getting more frequency content than we really need, which is very similar to what we were talking about here, that we are getting some additional copies over when we were just comparing the Fourier transform of a upsampled sequence and the original sequence. So the challenge that we are left with is that we need to, quote unquote, kill some frequencies. We are getting additional copies, we need to get rid of them. Now, in signal processing, getting rid of frequencies is very easy. We do filtering operation, and the frequencies that we don't need, we just multiply them with 0 in the frequency domain. So what kind of filter do we need? Let's take a look at it by explicitly comparing a specific Fourier transform. So we start with a signal xt, we sample it by sampling period t to get a sequence xn. The original signal has this Fourier transform, let's call it A, the height is A, and it's band limited to pi by t. So when we sample that, we get a sequence xn whose Fourier transform is given as follows. So this is the Fourier transform of my sample sequence x of e to the j omega obtained by scaling the frequency axis by factor of t and the scaling the amplitude by 1 over t. Now what we are saying is that let's take this sequence and let's now take the example of upsample it by a factor of 3 to get xe of n. And according to our derivations, what will happen is that we will now get back a Fourier transform where for the expanded sequence, we are going to get scaled version of the frequency axis, but the shifting will be by a factor of 2 pi over L. So if I do that, I'll get back the following. So I get a frequency scaled version of this. So I get this pi over t will go to pi by 3 and minus pi by 3. The height of this, according to this, there is a scaling of 1 over t, so the height is still a over t. And the endpoints are pi by 3 minus 2 pi by 3. And then what I see is that I get shifted versions by 2 pi by 3. So I will get another version of this shifted over here, and I'll get another version of this shifted over here. And of course, there will be then repetition of this beyond pi and minus pi. So this is what the Fourier transform of my expanded sequence looks like. And the issue here is that I have these 2 additional copies. So in this case, upsampling factor was 3. So I get 2 additional copies of this version. Plus, I don't have a factor 3 around here. In reality, if I really sampled something with a sampling period of t over L, then I should have the height should be 3a over t, or LA over t. So how do we fix that? Well, the answer is very simple. I can get rid of this additional copy and this additional copy by low-pass filtering my expanded sequence. So if I were to low-pass filter, so if I draw my low-pass filter over here, if I low-pass filter with a perfect low-pass filter with cutoff of pi by 3, what's going to happen? I am going to get rid of this copy, and I'm going to get rid of this copy, and I will only be left with a frequency scaled version of my original transform, which has the right scaling. I still need to worry about the magnitude scaling. Well, that I can do by using a low-pass filter which has a gain instead of 1. The gain of the low-pass filter is L. If I do that, then I will get back a sequence whose Fourier transform is going to be have the height of 3a over t. The cutoff will be pi by 3 minus pi by 3. And then I can have the same thing happen over here at 2 pi and minus 2 pi. Okay. So what this is saying is that if I actually do a low-pass filtering with a cutoff of pi by L and gain equal to L, if I do that, then I actually get back, in that case, get back a sequence xin, which is going to behave as if I had taken my original signal and sampled it with a period of t over L. Okay. So this example basically highlights how you actually combine your upsampler with a low-pass filter to get real interpolation. So let's recap the derivation. So the derivation is that if you want to do interpolation or increase the sampling rate, of a sequence, the way to do that is the following. You take the sequence, you upsample it by a factor of L, or expand it by a factor of L to get the expanded sequence xen. But that sequence is going to have a bunch of zeros. That sequence is going to basically have a sample, L minus 1 zeros, another sample. You need to fill in those zeros. And the low-pass filter, which we'll see in the next video, we should think of it as an interpolation filter. So once we take a low-pass filter with cutoff of pi over L and gain of L, if I take this low-pass filter, then I get XIN, and this is the interpolated signal. This signal, all of the zeros in between that we get when we go from XN to XEN, in this interpolated signal, those zeros would have been filled. In particular, if XN was obtained by sampling x of t using period t, then what happens is that xi is equivalent to samples of xn of xt. So if xn was obtained by sampling x of t using period t, the interpolated signal xi is equivalent to samples of x of t using sampling period t over L. And since L is an integer, effectively we are reducing the sampling period. So even though we never obtained those samples, by doing this interpolation operation, we are actually able to get back those samples if we were so interested. So this is the gist of, this is the interpolation expression. But while you do that, do not forget these other relationships, especially this frequency domain relationship for the expanded sequence as a function of your continuous time signal, and also this relationship between your original sequence and your expanded sequence. Those are all things that you should keep in mind, and we can then talk about, after this video, we can talk about basically interpolation or its interpretation in the time domain.